Today we are going to learn how to create a confidence interval for a mean. First thing you have to do is kind of understand what it means to have a confidence interval. So we'll start with some definitions to get us going. So let's say I want to get some information about a population, but the population's too big, I just can't find out this information from every single person. So what I might do is take a sample. And let's say I'm looking at the population mean. Then if I took a sample and got the mean of that sample, that would be a point estimate for it. It's an estimation of what I think might be representative of the whole population. So I could do this for a point estimate for a number of different things, and here's some examples that we've used in the past. So I could do it for population mean mu, and this is how I'd calculate x bar. I could do it for variance, and for proportion as well. And so there's some formulas here just to refresh our memories on what letters we're using for those and what formulas we use to calculate them. So point estimate's great and all, but maybe I want to have a little bit of wiggle room there. I want to know, well, maybe just an interval that I think the population is in based on my point estimate. And so that would be an interval estimate. It's a range of values that I think the actual parameter is in. Now, a confidence interval is a type of interval estimate that has a specified degree of certainty about how certain are we that that population parameter is in the interval. And so that level of certainty is our confidence level. Common confidence levels are like 90, 95, and 99%. Those are usually the ones we'll see. But it can be any value, really, any percentage. And over on the right here, you can see some examples of, let's say that I did a whole bunch of samples here and calculated a confidence interval based on each different sample. The confidence level tells me what percent of those confidence intervals should actually contain the population parameter. So here I can see the actual population mean going here, and all these blue intervals actually do have that value in there. So those worked. I do have a couple that don't have it in there. That is the nature of sampling. You're not always going to get 100% of them containing that population parameter that you're looking for. Okay, so how do we calculate one of these things? Well, here's an example to kind of get us an idea of all the parts of one of these problems before we actually calculate a confidence interval. So a random sample of 120 students from a large university yields mean GPA 2.71 with a sample standard deviation of 0.51. Based on this data, we have 90% confidence that the population mean GPA is between 2.63 and 2.79. So this is one that's already been calculated. We're just going to pick out all the parts of it. So that sample mean that we got from the 120 students, that is a point estimate for the population mean. The 0.51, that is a point estimate for the standard deviation. The 2.63 and the 2.79, that is my interval estimate. Somewhere in there, we think the actual population mean lies. Now, those two values themselves are the lower and upper limits of that interval, so we use those terms a lot as well. And the confidence level was 90%, which I may be using this in calculations, so I'm going to use the decimal form of 0.9 for a lot of these. So that's kind of the nuts and bolts, the parts of a confidence interval. We need a few more formulas, though, to get us to our final answer. The error. Now you notice on all those confidence intervals we showed in that chart, they all had a dot in the middle and then our lower limit on the left and the upper limit on the right. Well, that point estimate that you get from your sample will always be right in the center of your interval, and the distance from it to each limit on the outside will be what we call the error. So the error tells us how accurate our estimate is, and it's sometimes called the error bound or the margin of error. Has a lot of different names, but if you hear error, we're probably talking about the same thing. And the formula is going to vary depending on what you're measuring. Am I looking at a mean or a proportion or a variance? The formula is going to vary. We're looking at a mean today, so here is the error formula for a mean. with an unknown population standard deviation, which is pretty typical. If I don't know the population mean, I probably don't know the population standard deviation. But I will know the standard deviation of my sample, so I can use that instead. Once you have that error, to form that interval, you just subtract the error from the mean, the sample mean, to get the lower limit, and add them to get the upper limit. And if I want to write it in interval notation, here it is. Just the two numbers in parentheses with a comma separating them. Okay, let's do an example of this. You randomly select 16 coffee shops, and right away I'm getting numbers, so I'm going to start labeling them. So I'm going to 16 coffee shops. That's my sample size. So that's N. And measure the temperature of the coffee sold at each. The sample mean, there's my X bar coming, is 162.0 with a sample standard deviation of 10.0. So there's S. And find the 95% confidence interval for the sample mean. Assume that the temperatures are approximately normally distributed. So because they told me that it's normally distributed, I can use this nice normal curve right here. And I'm going to go ahead and call that confidence level C and put it into a decimal form. Okay, so that error formula, let's look at it again. I need to find a t-score. I've got S and N, but I don't have a t-score. And so to find that t-score, I have to realize that this confidence level I was given is a probability. It's a probability that the population mean is in my interval. And so I'm going to use that on my chart here, on my distribution. This 95% is the center 95% of my interval. And that should be a, well, let's try and make that symmetric. There we go. Okay, so this area in the middle is 0.95, so it's most of what's under that graph because the total area under a normal curve is 1. So I need to find the lot number, this TC on the right. And on the left is going to be the negative of that because these are symmetric. So whichever one's easier is the one I'm going to go with, the one I'm going to find, and then I can use that in my error formula. So whenever I do this in my calculator or in Excel, the function wants the area to the left of a t-score. So I'm going to go with the one that's a little easier to find, which is the left one. When it comes to plugging it into the error formula, I'm going to just drop the negative off because I will get a negative for this every time. Okay, so I need to find that area in the shaded region. And remember, the whole thing is 1. So if I subtract the 0.95 I'm given from the 1, then I get the area to the left of the negative t-score and the area to the right of the positive t-score together, the two tails. And I only want one tail though, but they are symmetric. So if I take that area and divide it by 2, I'll get just one of them. And so that's exactly what I'm going to do. I'm going to take 1 minus the confidence level and divide it by 2. I'm going to do the exact same thing every time. The only thing that varies is the confidence level. So if I plug that into my calculator, I get an area of 0.025. So I've got the area that I need. Now I just need to figure out what that t-score is. Now this is a t-distribution, and I have an area. That means I'm going to need the degrees of freedom, which is 1 less than the sample size, so 15. And I've got all the parts now, and I just need to know what function I'm going to use, and that is going to be the inverse t. So in a calculator, it's inverse t. In Excel, it's t dot inverse. We're going to run through both of those real quick and see what our t-score is. Okay, so in my calculator, I'm going to go second distribution, and I want number 4, the inverse t. I plug in my area and the degrees of freedom and paste. And oh, it's thinking. And there we go, negative 2.131. In Excel, I'm going to come in here equals t dot inverse, grab it off this list here. The probability is the area we calculated and the degrees of freedom. Make it the same thing, negative 2.131. And so I wanted the one on the right. I just found the one on the left. So I just dropped the negative off, and I have the t-score that I need for the error formula. Okay, so we cleared some stuff off our screen now. I've got all the stuff I need, and I've got my error formula, and so I'm just going to plug everything in. So plugging all that into the error formula, I get an error of 5.33. We're on the home stretch now, just a little bit left to do to get our final answer. If I take that sample mean, the 162, and subtract it from the error, then I get the lower limit of my confidence interval. If I add those two numbers, I get the upper limit of the confidence interval. And then if I want to put this in a little more context, I'll put it into interval notation, and I'll throw in the units as well. And I rounded this to the tenths place because that's what the information I was given in the problem was rounded to, which is generally a good rule of thumb. Whatever the values are rounded to, that's what you'll round your final answer to. Just be careful not to round any intermediate values, like this t-score, to the tenths, because then your answer could end up being way off. Now, we did all this work, but what does it mean? Well, we don't ever want to forget that last final step of this, which is writing out our interpretation of what that interval represents. So when I'm interpreting my confidence interval, there's a few things I always want to make sure that are in there. I want to make sure I include the confidence level that I used, explain what that population parameter was. It's the mean. It's the mean of what? For us, it's the mean temperature for coffee. And then the actual answer, of course, we want the confidence interval in there. You can just use this statement as a nice cookie cutter every time. So we estimate with some confident level of confidence, that the true population mean of blank is between these two values. So let's see what that looks like for our example. So let's see. So we've got our interval, and so we estimate with 95% confidence that the true population mean temperature of coffee sold at coffee shops is between 156.7 degrees Fahrenheit and 167.3 degrees Fahrenheit. So it puts all the relevant information all in one place, and we have our final answer. These two things are my complete final answer for this problem. This has been so much fun, everybody. I'll see you next time.